Please give a warm welcome to Miren, and she's going to introduce the people.
Hi everyone, I'm Miren Urteaga. First of all, thank you for coming. Thank you for inviting me. Yeah, actually, it's the first talk I'm giving in front of you. So weirdly enough, yeah. So I'm Miren. I'm the product manager of the Samsung's new voice assistant Bixby in German. I proudly say our voice assistant speaks better German than I do. So yeah. In my talk, first of all, I will talk a bit about this paradigm shift that we are experiencing with new technologies coming non-stop on the market. Then I will, I'm a linguist, so from a linguist perspective, I will tell you what actually is voice interaction, how we talk, how we speak, and so on and so forth. And then I will briefly talk about the technologies that we use in natural language processing to achieve that human communication. So I know this is a very new topic, like voice assistants. Oh my God, they're spying in my living room or something like that. A lot of people are very reluctant, and I understand why. But technology is constantly evolving, and we are introducing it in our lives without hardly even noticing. And when we look back, sometimes we don't even remember how it was before before the technologies that we use existed. For example, now I'm going to present you two pictures that were taken in the same street 8 years apart in a very similar event, okay? So this picture was taken in Via della Conciliazione in Rome when John Paul II died. And you see everyone mourning the Pope, oh, the Pope has died, there. And the next picture was taken exactly in the same street 8 years apart when Pope Francis was elected. See if you notice the difference. So technology is creeping in into our lives, and it doesn't have to be bad. It's just a way, we are just generating new tools to communicate or experience the world better, or to access the world's information better. And that's, at the end of the day, that's exactly what voice assistants do. They give us access to information in the world in a faster and more natural way. So, but one thing I have learned during my career in academia or in industry or in research centers is that no matter how much you know about languages, no matter how good of a linguist you are, no linguist in the world knows how we talk, how we speak, how we learn languages. So how do we teach computers something that we don't understand fully ourselves? And that's the biggest challenge. But we can all agree that the following steps is what makes human voice interaction. First of all, we need to hear a sound wave, kind of. Then we have to understand it, which is not the same. I can listen to Chinese, but I will not understand a word. Then produce a response to it, and then utter it. I understand French very well, and I can even think about the response, but I am unable to speak it out, for example. And if you look closely, in natural language processing, we have the exact same counterparts, and machines do these steps in a way. So for hearing, we have automatic speech recognition. For understanding, we have natural language understanding, which would be extracting the meaning of the words of the sentences. Then we have to prepare a response to what the user has said, and then the machine has to kind of utter it out. Chatbots usually give you the written response, but in a voice assistant, it's very important that it has to be voice experience end-to-end, so you need a very good TTS, speech synthesizer. So now I will walk you through each of the technologies from our perspective at least. So in ASR, here the objective is to teach the machine how to transcribe a sound wave into a written sentence. And to do that, we encountered a huge challenge first, which is language variability. It's considered that a human being does not utter the same vowel twice in his life. So we may think, no, I just said A two times. No, you didn't, because maybe in a very high frequency there was some glitch or whatever. So how should a machine just have a clear image of what a vowel is? To do so, we start by defining a phonetic alphabet. This is the German phonetic alphabet, but then, of course, if you define only the German phonetic alphabet, the system is not going to be able to, for example, understand happy birthday. The sound doesn't exist in German. So there is always a big discussion when defining the alphabet. And then we also feed a lot of transcribed audio corpora, basically transcribed, so audio corpora, audio texts that are transcribed phonetically, so the machine can map the sounds to the phonemes. But of course, if we only feed that to the machine, and we learn from that only, we would have a long string of phonemes. So you remember when you were children, and I had struggles at least, that when I was learning to write, I didn't know when the words ended, so I wrote everything together. So we have to now teach the machine to cut the string into words. And to do that, we feed them, language models. Language models in form of text corpora cut into engrams. So very briefly, what is an engram? An engram is basically a string of words. It could be a 2-gram, a bigram, a string of 2 words, a 3-gram, a string of 3 words, and so on and so forth. And what we do is we give a statistical value or a statistical weight to each engram. So they have, and that tells us not only how likely it is for a word to happen, but also how likely it is for a word to happen given the previous word. So that way, without giving any linguistic information, the machine knows that ich goes with habe and not with hast, because it's more likely, so the probability is higher that ich goes with habe. So imagine that the machine transcribes phonetically the following sentence. Maybe any fellow linguist? No, okay. Yeah, good, it's good. So such a string with a vowel in the beginning and an African in the second place, it could be, chances are it's the word ich, but then it's haben. What is that? I don't know. Okay, let's try haben, but that has a very low probability, so let's go with habe. Oh yeah, that has a bigger probability, so let's go with habe. So, and so on and so forth, we complete the whole sentence. And that is how very, ASR works. So now we have transcribed the sound wave into a written sentence. But now we have to extract meaning out of it. A sentence just written doesn't mean anything. And here is where the big revolution has happened. Like 10 years ago, 15 years ago, everything was based into keyword recognition. It was just, okay, if you understand this keyword, then do that. But words, even if they are listed in dictionaries and you can check the meaning of them, words, their meaning is very, very variable. It depends completely from the text, from the surrounding text, from the context. So the big revolution now happening is that we've gone from keyword recognition to intention recognition. I will give you an example. So imagine we have a user that has a super smart home and has arrived home, but the windows, the sun was shining and it's super, super hot at home. So he says, it's so hot in here. And if we had a system that only recognized keywords and recognizes the word hot, to say, oh, hot, hot, let's make it hot, and turns the heater on. So because here now hot alone doesn't mean anything. You need the whole sentence to understand it. So in intention recognition, we analyze the whole sentence, and there we recognize that the customer or the user is actually complaining that it's hot, so we turn the air conditioning on. And to do so, in Bixby at least, we work with corpora in whole sentences, so we do the analysis of the whole sentence, and we mark the parameters, and the machine, so the algorithm learns from the whole structure. It's not word-based, it's sentence-based, it's structure-based. Syntax is very, very important in our system. So once it's well trained, the system will, when you feed him a training sentence, it will create this kind of trees that analyzes the data and the parameters in it. So now we have our sentence transcribed, we extracted the meaning out of it, then we have to prepare a response. For natural language generation, I have to say our voice assistant, and I don't think there is any in the market that is proactive. We are not proactive. Proactive means that the system talks to you before you even address it. So we work with templates of sentences, which is not real natural language generation. Natural language generation, like the real thing, is AI poetry and so on. There is this kind of things, but we don't do that. We think it's annoying that, you know, every day, hello, this is your AI poet, and yeah, poem of the day, and yeah, it would be too much. So we just use like templates of sentences, and we change slots in it depending on the context. So if we want to turn the air conditioning on or off, we just change the verb. So it would be like slot filling. And then once we have the response ready, we have to speak it out. We have to read it out. And here again, the biggest problem is variability. Yeah, because as I said, we always use very, very different sounds. And if we make it always sound the same, it just doesn't sound natural. So how do we overcome it? With the biggest corpus that you can build. So you can get an idea. In these two sentences, the one in declarative form and one in interrogative form, it's an inside joke for linguists, but there is no linguist, sorry. There are in color, for example, in the word color, you have those O's there, but those O's are very different from the O's uttered in the second sentences because of the prosody of the sentence. So that means basically that you need as many samples of sound in different places of the sentence, surrounded by different vowels, consonants, whatsoever, to make it sound natural. For Bixby, we built a corpora of 33,000 sentences that were then taken to a recording studio, and a voice talent or an actor was chosen, and she recorded these 33K sentences she was there for 6 months recording. But the voice is very good. So basically, in the end, when we have the sentence that we want to utter, we build this big corpora, we record it, we split everything into different sounds, and when we have to synthesize a sentence, we just go, okay, I need this consonant, I need this vowel, and so on and so forth, and we build this sentence. And then another layer comes in order to make it sound smoother, and we speak it out. I know there are a lot of initiatives now to make it, you can actually build a synthesizer quite fast with a way smaller corpus, but to make it market ready, to make it sound really natural, you need, the best approach right now is just power, just feed in a lot of data. So yeah, basically we put a lot of oral corpus and read it out. So cool, everything is very cool, very flashy, but what do you do with it? We are happy to announce that we already developed, so we already launched the Bixby developers website. Here you can download the IDE of Bixby and you can build capsules. In Samsung they are called capsules, others call them skills. It's the same, okay? So yeah, you can build a capsule for your company, for your whatever, for yourself, and yeah. Now still you have to contact Samsung in order to upload the capsule, but hopefully soon you can do it on your own. And that is everything. Thank you. Oh, yes. Questions.
We have time for questions. Sorry, yeah.
There's one.
Yes. Yeah, we have so many questions. Oh, okay, we can only take 2 or 3, so keep it short. Remember, questions are not about yourself. And who's first?
Olaf Mackert, hello, Connector. Where can we have developer access to your fantastic speech recognition?
To the what?
Developer access, yeah, to implement some cool stuff with it.
Here.
Fantastic, thank you.
Thank you.
And it was short and brief. So.
Test. All right, thanks for the presentation. My question is, so you focus on Bixby in German only?
Not only, I mean, we are in charge of Bixby in German, but Bixby has been launched in 5 languages. Exactly,
but I mean, well, you personally focus on Bixby in German primarily. Yeah. Considering there's Bixby in many languages, how easy is it to shift features, intelligence from one language to another? Or is it completely detached systems?
Okay, this is welcome to the natural language processing. Natural language processing has been developed for over decades in the US. So the core technology actually is English. However, and is token-based, which has implications later on. Bixby was not developed first for German. It was developed first for English, Chinese, and Korean. And German came like 1 year later or something like that. So for NLU, so for ASR, you have to build the databases from scratch for any language. For NLU, we use the same core technology. It's a random forest neural network that does everything. And it is quite translatable. Of course, you always have problems with compound words and so on and so forth in German. Or like, in German we have to use marked up languages to identify the gender of the words and so on and so forth. To say if it's one could be S10 or Esther or whatever. My German is not so good. So, yeah, in German we do need help of other technologies like marked up languages that in English you don't, but the core technology is actually the same.
Yeah. Thank you very much. I think if you have another question, Miren is around, so she's happy to answer questions during the barbecue.